Now, Wikipedia defines data science as a concept to unify statistics, data analysis, and machine learning in order to understand and analyze the phenomena of data. But what better way to test these techniques and theories than to employ them in actual real-time data science projects? Hi all, I'm Upasana from Edureka, and today we shall be talking about data science projects and how to approach a problem in data science. But before we begin, let's talk about the topics we shall be covering today. So first of all, we'll be talking about the basic approach to solving a problem in data science. Then we shall have our first data science project, which is based upon decision trees and random forests. So we'll be talking a little bit about those concepts as well. Then we'll be talking about our second problem, which is based on regressions. So we shall be discussing those concepts. And finally, we'll be summarizing what we learned in the entire session. Now, before I begin with the details of the project, I would like to tell you my aim for today. It's not really dealing with large data sets and doing parallel progressions, but I want to take you through the basic steps of how data scientists on a daily basis deal with problems. Yeah, so without much ado, let's get straight into the module. So the basic approach to solving a problem in data science. So after you frame the problem, the first thing you do before solving a problem, before any of the steps, is to define what exactly your problem is. Next, you collect your raw data which you need for the problem. Then you process and clean the data, you transform the data. Then you perform exploratory data analysis on it, you explore the data, you group the data the way it's supposed to be grouped. Then after performing this in-depth analysis, you build a model. You build a prediction model depending on what you require of your data. And finally, you communicate the results of the analysis. Yeah, so today with both our problems, we are going to be doing just that, but with two different approaches using two different algorithms. So let's move on to the first problem, shall we? So this is our first problem statement. The quality of wine depends on a number of factors such as taste, fixed acidity, volatile acidity, a bunch of different factors, yes. So we are given a data set containing 50,000 samples of a wine from a winery, and we have to draw a prediction of a quality of a sample based upon the given information. So first, let's read the data and explore it. Yeah, let's just see what data do we have. Now we are going to be taking a random forest approach for this problem. So let's talk a little bit about decision trees and random forests. Now decision trees are inherently different to monotonic transformation or nonlinear features. So this is different from your nonlinear correlation among predictors because they simply cut the feature space in rectangles or hypercuboids, which can just adjust themselves to monotonic transformation. Since decision trees anyway are designed to work with discrete intervals or classes of predictors, any number of categorical variables are not really any issue with the decision trees. So models which you get from your decision tree is fairly intuitive and easy to explain in business. Probability scores are not a direct result, but you can use class probabilities assigned to terminal nodes instead. So this brings us the biggest problem associated with a tree model. That is, they are a highly biased class of models. You can make a decision tree model on your training set which might outperform other algorithms, but it will prove to be a poor predictor on your test set. So what do you do about it? You basically create a random forest. So the problem of overfitting is overcome to a large extent by using random forests, which are nothing but a clever extension of decision trees. Now this problem of overfitting is overcome to a large extent by using random forests, which is nothing but a very, very clever extension of decision trees. Now the algorithm of a random forest starts by building out trees similar to the way a normal decision tree algorithm works. However, every time a split has to be made, it uses only a small random subset of features to make the split, instead of a full set of features. It builds multiple trees using the same process, and then takes the average of all trees to arrive at a final model. Now this works by reducing the amount of correlation between trees, and thus it helps in reducing the variance of the final tree. Yeah, so let's go to RStudio and get started with the project. Now this is a fairly small code, but it will explain exactly what we are doing step by step, and it is pretty easy to understand. That's why I've picked this data set. So let us first read the data and explore it. So we can read the data directly from the page, or you can do what I have done by downloading the data. You can use the read.csv command and put in your location right here, and your file shall be read. I've already read the file and assigned it to a variable called wine. Next, you can view your variable, which is your entire data set, your control and enter, which you use to run the line. This is what your data set looks like. You can see your various parameters on judging your wine, your fixed acidity, volatile acidity, citric acid, residual sugar, chlorides, sulfur dioxide, total sulfur dioxide, and we have pH, sulfates, alcohol quantity, and quality. So getting back to our code, let's run this line by line. So your head command right here will give you the first few rows of your matrix, which in our case is our table. It has put them in like 2 parts because there were too many columns. Yeah, you can see your fixed acidity, volatile, citric acid, residual sugar, so on and so forth. Yeah. So let's build a bar plot around this. So this is a bar plot regarding only one column, which is the wine quality. I'm going to zoom into this so that you can get a better look of it. As we can see, there are a lot of wines with a quality of 6 as compared to the others. And the dataset description states that there are a lot more normal wines than excellent or poor wines. For the purpose of this discussion, let's just classify the wines into good, bad, and normal based on their quality. Yeah, so your normal being 6, your bad being below 6, and your good being above 6. Yeah, so let's do that. So here you see we've gotten our numbers. We have 1640 bad samples, 1060 good samples, and the normal samples amount up to 2198, which is basically what this bar plot was also showing, your normal ones being way more than the good and bad ones. So this has classified all the wines into a good, bad, normal, depending on whether their quality is less than, equal to, or greater than 6 respectively. So let's look at the distribution again. Yeah. So before we build our model, let's separate our data into testing and training sets. So we're going to use this set.seed. Okay. So as you can see here, this has placed 60% of our observations in the original dataset into train and the remaining 40% into test. You can see it in the global environment right here. Now we are ready to build our model. We will need the random forest library for this. So install packages and then you call the library. It will take some time to install the packages, and once it's done, here it's done. Now we've also called the library, so we're going to create a random forest and assign it to a variable called model. Now we can use ntree and mtry to specify the total number of trees to build. By default, let's take it as a 500, and the number of predictors to randomly sample at each split respectively. So let's take a look at our model. So here you can see that we've called our model. Right here you can see the details of it, good, bad, normal, and the error in each class. It's all given right here. So we can see that 500 trees were built. Yeah, number of trees 500, and the model randomly sampled 3 predictors at each split right here. It also shows a matrix containing prediction versus actual, as well as the classification error for each class. This is right here. Okay, so now let's test the model on the test dataset. Okay, let's just select it. And we can also test the accuracy like so. We can do an en-row test on it. These are the total number of good, bad, and normal, as you can see from the table. And there we have it. We've achieved 71.5% nearly in accuracy with a very simple model. It could be further improved by feature selection, but that's a session for another day. So let's move on to our next project. Now we are going to be using regressions for our next problem statement. Let's read out the problem statement first. So an individual's annual income results from, say, various factors intuitively. So it's influenced by the individual's education level, age, gender, occupation, etc. So we are being given a UCI adult income data set. So we'll try to predict the salary class of a person based on the given information. So we can explore the possibility in predicting income level based on the individual's personal information. For this, we shall be using another method called logistic regression. But first, let's know a little bit about regressions in general. So basically what a regression means is that suppose you have a column, which is your dependent or predicted variable, and you want to categorize it as a bunch of independent variables. Yeah, it is the most prevalent algorithm for solving industry scale problems, although it might be losing its ground to some other techniques in terms of efficiency and implementation. It's a very convenient process to use and is the most used algorithm. It's a very prevalent algorithm. So a very convenient and useful side effect of a regression is that it does not give you a discrete output or an outright class as an output. Instead, you get probabilities associated with each observation. Then you can apply many standard or custom performance metrics on this probability score to get a cutoff and in turn classify output in a way which best fits your business problem. Also, these regressions are very efficient when it comes in terms of time and memory requirement. It can be applied or distributed data and also has an online algorithm implementation to handle really large data on less resources. So with that, let's move on to our project number 2. So since this is a comparatively longer program, I've kind of segmented it down to all its steps. It's easier for me to find out snippets from it, and also it will be easier for you to understand where we are. So the basic approach is going to be the same. We are going to clean the data, transform the data, do some EDA, and then build a model. Okay, so let's start with some acquiring data. As usual, I get the data from its location and put it in a variable called adult, and then I view the variable, the same thing that I had done the last time. There you go, this is our data. From the structure output, we can see that you have age, work class, your education, your marital status, your occupation, relationship, a bunch of other variables. Yeah. Then we are going to use this command str, which basically is an alternative to your summary command in R. Here it gives you a summary of your entire data set. This is your summary of your entire data set, your education, education number, race, gender, a bunch of other things. Now let's just clean our data a little bit. So from the structure output, we can see that some of these columns have a really large number of factors. We can clean these columns by combining similar factors, thus reducing the total number of factors. Wow, said factors a lot of times. So let's go ahead and do that. First, we bring in a table of summarizing all the columns. Then we're going to combine our like factors. Here you can see it shows you the total number of federal government officers, private, self-employed, and unemployed adults. Now, we can also reduce these factors into married, not married, and never been married. Yeah, so let's do some marital status combining. So again, it shows the number of people that have been married, never married, and not married. Same old, same old. Now we're going to do this a bunch of different times, combining them by country and region. Remember, the more efficiently we group it, the easier it's going to be for our regression to carry out. And then we are going to call for a summary. There you go. There we have it. We have Asia, Europe, North America, and South America, and others. So there are a lot of countries here, and we have basically reduced them to their respective regions. Now we can revert the altered columns back to factors since we've had to change them into characters. And that's why we have used your summary. Next, let's deal with the missing data. Now during data cleaning, we can see that there are some values with just a question mark. We can convert these values into a not applicable cell so that we can deal with it in a more efficient manner later. Now we can create a missingness map to get a visual idea of where there are not applicable values in the data frame. For that, let's first put it into a data frame. Okay, now that's done. Now to use mismap, we have to install a package called Amelia. Let's install the package and the library. Now I'm putting on labels I'm putting on the background as a black, and we're going to have our lines in yellow. It's going to take some time to run because it's a lot of data to process. You have to be a little patient here. All right, let's zoom into it and see. So what the missingness map does is it arranges all of these categories into descending order of how many not applicables are present in each of those columns. Yeah, so let's go back to the code. Now in the mismap, we can see that all the not applicable values are found within the occupation and the work class columns. So we will choose to omit these values since there are only very few of them. So let's do that. Okay, it's done now. You can see no yellow lines here. Yeah. With that, let's move on to some EDA. So first we shall plot a histogram of ages that is colored by income. Alright, so for that, let's install ggplot2, which will give you an access to a bunch of different visualizations, really cool visualizations. Once you install it, you can just call it whenever. Alright, seems like it's been installed. Okay, now let's plot the ggplot. Let's call for a histogram. Okay, let me zoom into this to get a better look. Now here the coloring is indicative of percentage. So from this plot we can see that the percentage of people who make above 50k, that's in pink, peaks out roughly around 35% between ages 30 and 50. That is right here. Okay. Now next we shall plot a histogram of hours worked per week. So aesthetic, and then from this, you can see it is clear that the highest frequency of hours worked per week occurs at 40. This one right here. So next, let's find out what is the income class by region. For that, first we need to change the name of the country column to region. So let's do that. First, let's just install a package called data table so that we can use this setNames function. Okay, now our native.country has been changed to region. So now we're going to reorder the factor levels by count. So let's reorder and then get a plot. All right. As we can see, North America, there are a bunch of people. There is maximum number of people who have an income less than equal to 50k, and it still has a decent amount of people who earn more than 50k, but this number is massive. And then you have your Asia, other countries, Europe and South America, which seems to be a pretty small graph. So next, let's build a model to this. So the purpose of this model is to classify people into two groups, below 50k and above 50k in income. So we'll build a model using training data and then predict the salary class using the test group. So first, let's train and test split. Let's split it into training data and your testing data. So we're going to install a package called CA tools and call it using the library. All right, it's been installed and called. So now we're going to split our sample in a ratio of 70-30. Alright, our training data, as you can see here, and also as I had mentioned the last time, you can see our training data here is nearly 70% of the observations and our testing data is 30%. So training the model. So basically we've broken down the code and now we are going to train the model. So let's talk about this line for a second. So let's break down the code for this particular line. So GLM is generalized linear model that we will be using. Your income, this right here, means that we want to model income using every available feature. This particular part. Now this family equal to binomial is used because we are predicting a binary outcome below 50 or above 50k. So basically we are just training the model. Next is our prediction. So here we are initializing predictions on the test data using our logistic regression model, which is this log.model. So we specify type equal to response right here so that we get predicted probabilities instead of probabilities on a logistic scale. All right, so let's run this code and see. Next, we can compare our results using a confusion matrix. Since our predictions are predicted probabilities, we can specify probabilities that are above or equal to 50% as true, and anything below 50% will be false. So let's call for a confusion matrices. You can see the confusion matrix right here. From the confusion matrix, we can determine the performance of our model. So how close are the predicted values to the true values? Let's check the accuracy. The same thing we had done previously. Take this add. So while we are at it, let's also just calculate the true positive rate and the precision. We can see all of that at the same time. So as we see, we are nearly 85% accurate, and the true positive rate turns out to be 88, and we are about 92% precise with our model. And it's a very simple model. It could be further improved by a few other algorithms, but this is still pretty precise. So basically these two terms, both precision and recall, are based on an understanding and measure of relevance. In statistics, if the null hypothesis is that all terms are irrelevant, which is basically a hypothesis is being rejected on the basis of number, it corresponds respectively to the maximum number of precision. Precision can be seen as a measure of exactness, of quality, whereas your recall is a measure of completeness of quantity. That's why we have calculated both of these values. Let's summarize what we have learned in this session. So in this session, we have talked about the basic approach towards a data science problem and how to go about it. We talked about decision trees and random forests and concepts around linear and logistic regressions. We also worked on 2 different projects and built prediction models or data models using the basic concepts of supervised learning. So with that, I conclude my session. If you have any doubts, any queries, feel free to leave them in the comment section below. Thank you and have a great day ahead.